my wonderful students, let me have your attention. I have a migraine headache, and my so if I don't appear that comfortable up here, that's why I'm groaning and moaning up here if I do. But hopefully, uh, if I could just teach in a completely darkened classroom, it would really help. But we can't quite do that. So, all right, um, we're going to talk about the electromagnetic field and kind of follow up with what I talked about concerning Michael Faraday and his discoveries, James Clerk Maxwell and his mathematical developments and discoveries. Um, and we're going to do that so that we can figure out molecules in the periodic table. Now, we've got two regular lectures coming up. You might want to jot down this little mini calendar here. It's 3 weeks. We're in the last full week of lectures. Right up here, magnetic field at atoms, April 19th. That's where we are today. Tomorrow, no office hours. But next Wednesday, mega office hours. So I'll pay you back office hours wise next Wednesday. We'll talk about de Broglie and the periodic table on Thursday. And we're going to have homework tonight. We'll have regular homework over the weekend, due next Tuesday. But we'll also, over the weekend, have a bonus mega review homework. Okay? So for those of you that have not bagged any bonus point activity, you can all get it. Now, you might have 30 review questions in this mega review homework, but you won't be getting 30 bonus points. But I'll boil it. I'll scale it down to 2 or 3 bonus points maybe, and that'll be helpful. That'll be almost like going to an SSG session. So that'll be this weekend, and that will run. I'll probably set the mega review homework, bonus homework, for more than 4 attempts. And I'll have it due Friday of finals week. So you have plenty of time to use it as a study tool. All right? And which is why I give that out to you. Special study group signups will start running, I hope, next Monday night. And it'll be very similar to the way we've done it in the past. On Tuesday, I'll give you a lecture about Mendeleev's orchestra. And then in class, we'll have another bonus point activity. And that is my traditional. Please pay attention. I'm suffering up here very difficult pain, and I don't want to be frustrated on top of that by yelling at you guys. So next Tuesday, a week from today, we'll have maybe 30 minutes of regular lecture, and then about maybe 45 minutes or so of a review. The review will be a clicker activity. It'll be for bonus points. And it will be like on exams, you have a clicker page, and usually you have maybe 2 or 3 questions, 4 questions, some calculations and stuff usually, but occasionally some multiple choice. On the mega review next Tuesday, you'll have something similar, but it might run 20 questions, 30 questions. But you go through it the same way you go through the uh, clicker items on a test. And so it'll be pretty nice. So that'll be our semester review. Kind of gets you another thing that you can use as a study tool. You'll have the handout. You'll work from a handout. And Darian and Caroline and I will be circulating around, or you can come up here and consult with me and stuff like that. And you just work on that stuff. And you can keep the handout. Okay, it's kind of like a nice little mini study guide type thing for the final. And then on Wednesday, that's UCF Study Day. I'll have mega office hours. Special study groups will be running. Those of you that are special study group leaders, what we want to do, I believe, when I first mentioned it to you, is Tuesday, Wednesday, Thursday, and Friday of exam week. Okay, so you'll be running special study groups in here at whatever time and place of your choosing, as you may decide yourself. Can be a completely different place, and you'll have possibly a completely different roster of students. And of course, it will be a different day. And then now this little note on April 30th, you guys can ignore that. That's for the online class. But your guys' final is 10 a.m. on May 3rd. Now that's 2 weeks from today. And the time of the final is 10 a.m., not 10:30. Right? So do not blow it. Do not come in 30 minutes late. Because if a lot of you need all the time that you get. And if you blow 30 minutes at the front of it, that's what we call SOL, toast. All right? Burnt toast. So don't do that. For those of you that are, oh man, sorry. Just the thought of newbies, magnified my headache like about two and a half times. For those of you that are freshmen, my advice to you for finals week is the following. And you're going to say, Dr. B, what do you know? But my advice is, sleep is a weapon. Sleep is a weapon that you must use. Sleep is your friend. Do not stay up all night studying at any time. Study hard, but not all night. It will degrade your performance the next day. Right? And you don't want to do that. When I was an undergraduate, we had this guy that stayed up all night, or like 2 nights in a row, two straight days. This is a legend at the college I went to as an undergraduate. And he stayed. He had an economics exam, econ. Microeconomics or something like that. And he stayed up to two whole days. And I forced him. So he got to the exam and he took out his blue book, and the professor hands out the exam, and they start working on, and he's writing. He's got a little blue pen, he's writing, and he's flying, he's blazing, he's on the move. And he finishes the test, and he hands it in, and he goes, I don't know what happened after the test, but I did find this out. I did learn this, and I believe that it's not a legend. He was so out of it, right, that he wrote in his blue book, he wrote down all the answers, beautiful essays, except he forgot to turn the page. So the first page of his blue book was one big blue blur. And you couldn't read any of it. And the guy took an F in that class. Do not let that happen to you. All right? Now I was not there. I was not a buddy of this guy. He was a year ahead of me. But I heard that this is the case. And he's a famous guy now. But I'm not going to tell you his name. You might not like it. Okay, special study group leaders. Send me your info meeting as soon as possible. Date, time, location. By the way, special study group leaders, make a note of it. Oh, boy. My office hours next Wednesday will be 9 o'clock to 12 noon. Do not schedule your special study group on Wednesday morning. All right, Shai, what is your review? Tuesday night? Wednesday, 12:30 to 2:30. Okay, yeah. So I'll be doing. So that's good. My office hours will terminate at 12, and everybody can scamper over to student union in the ballroom. Okay, so special study group leaders, don't do anything on Wednesday until 3 p.m. after Shai goes. Okay, don't set it up for my office hours. Don't set it up for Shai. And Darian, are you going to have office hours that Friday? No. You're Monday, right? Friday? Okay, you're going to have, and don't set it up noon to 1, right? Do not set it up noon to 1 on that Friday. And Caroline, I'm guessing, is going to run Monday. For her office hours, so don't set it up for that. Identifying features, so make sure because the students that sign up, they might not know who you are, so you have to have like your lucky fishing hat or something like that, or even just the textbook. Well, wait a minute, that won't work because we don't have an actual physical textbook. So you might have to go with your lucky sneakers or whatever you want to do. A sign-ups procedure will be the similar. It'll start Monday evening. We'll go in waves again. So it'll be open for general mass consumption at 10 p.m. And hopefully by Friday, Saturday, we'll have the schedule all spelled out, and you can look it over the weekend and kind of figure out your strategy for what to click on. Any questions about that? The entire next 2 weeks, schedule and so forth. Okay, let's keep going. I want to talk about the units of measurement for electromagnetism. The metric units of electric charge. Basically, it boils down to a count of how many extra electrons, in the case of having negative charge, or how many extra protons, in the case of having a positive electric charge. And that is because the smallest charges in nature that we can isolate and work with are electrons and protons. And they have the same charge value, but one is negative, the electron, the other one's positive. Okay, for large amounts of charge in the metric system, you use the Coulomb. The abbreviation is capital C. For small amounts of charge, so for instance, if you're working with electrons or protons, if you're working inside the nucleus, or maybe you're fooling around with molecules, a more conducive, a more congenial unit of measurement is the elementary charge, for which the abbreviation is lowercase e. And E is considered to be the charge on one proton, basically because the proton is positive and the electrons. So, in order to have positive numbers everywhere, we just use the charge of the proton. But the charge of the electron is the same size. It's just negative of the proton's charge, the opposite. Okay, now what that means is that 1 Coulomb of charge is about 6.24 times 10 to the 18 fundamental charges. So that's a lot of protons. Okay, let's figure out what that is. 10 to the 3 is 1,000, million, billion, trillion, quadrillion, quintillion. So this is 6.24 quintillion protons in 1 coulomb. Minus 1 coulomb, Courtney, would be the same number of electrons. And students, this is an everyday size measurement of electric charge. Now, a coulomb is a lot of charge. An everyday charge load on something like, in your car, you have a blinker, and your blinker has an electronic device called a capacitor. And the capacitor will have a charge capacity of maybe a microcoulomb of charge or a millicoulomb of charge. It would have to be a really big one to hold a coulomb, 6.24 times 10 to the 18 electrons. But you can do it. So what that means is that the electron, or in this case the proton, the fundamental charge, 1.602 times 10 to the minus 19 coulomb. So you can see that in scientific notation, the household size unit, the coulomb, and the atomic size or nuclear size unit, the elementary charge E, there is a huge range in sizes. 10 to the minus 19, 10 to the 18. That's a big range in the number of charges. But that's the two metric units that we customarily use. And there's other ones, but now here's another page that I'd just like to show you. This is from the National Institute of Standards and Technology. This is the value of the elementary charge, the charge on the proton. Well, and you can see that they've got it measured here. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 significant figures. They've really done a very precise job. And the plus or minus is down here in the last two, the 10th and the 11th digits. So, but yeah, that's so if you go to nist.gov, you'll be able to see that. All right, now the reason that I'm giving you this little blurb about elementary charge and coulombs and stuff is because we have to define the electric current unit of charge, or the unit of measurement for the electric current. And in the metric system, it's called the ampere, after a French scientist named Ampere, who figured out actually a lot of the calculus in 3 dimensions and 4 dimensions of the magnetic field. Professor Ampere, about 150 years ago, maybe. I don't know, I can't remember, 1800s for sure with this guy. The colloquial term is amp, and basically this one measures not how many have you got, but how many are going past a certain point in space per second. All right, so how much charge past a point in space per second. And so 1 ampere of current is 1 coulomb of charge per second. So if you think of your wire here, here's point P down here at the bottom, at the left end of this wire. If you think of that as your point at which you measure the current, basically you're taking into account, how many electrons are moving down that wire. All right. The ampere is a lot of current, and it can kill you dead, permanently dead. So when you see, for instance, in your house or your apartment, you may have a circuit breaker box, your car, and actually I think some car circuits have amps and more than 1 amps. Anybody know about that? Anybody fool around with their fuses and stuff in their car lately? I think they, uh, I think they measure car fuses and stuff in amps. And what that means is the circuit breaker will disconnect if the current goes above 1 amp, or the fuse will melt and the circuit will break. Current will not flow if the current goes over 1 amp. They have it designed that way. Okay, so you have to be really careful about it. Now the current, the symbol for current is customarily capital I. Sometimes in the electrical engineering department, you'll see lowercase I. But it basically depends on the speed of the electrons, how fast they're moving in the wire, or how fast they're moving through space. You know, if you're over by the surface of the sun, they have big, huge currents moving through space. They don't have wires, but they have big, huge currents of charged particles in the atmosphere of the sun. They follow the magnetic fields, you know, the looping magnetic fields of the sun. So it depends on the speed and also the distribution. You know, how many are there? You know, how closely are they packed together? So if you have, you know, like a buffalo stampede, you know, you have a speed and a density of buffaloes. How many buffaloes per acre? And how fast they're moving. Now, if you only have one buffalo per acre, it doesn't really matter. You can dodge it. But if you have 10,000 buffalo per acre, you better head for the hills because you're going to get trampled. Okay, same thing here with current. The density or the spatial distribution of the electrons. And in wires, just you make a side note, in most wiring and electronic devices, it's the electrons that flow. It's not the protons. Because protons, sorry, I didn't make a note of this earlier. The mass of the proton, you can write this down, the mass of the proton is about 2,000 times the mass of the electron. Let me repeat that. The mass of the proton is about 2,000 times the mass of the electron. So the electron is teeny. And in a wire, the things that are moving are electrons. Now the protons will move, you know, they'll oscillate a little bit, but the things that actually move from point A to point B are the electrons. Side note number 2, the mass of the neutron is also about 2,000 times the mass of the electron. So neutron and proton have about the same mass. Very close. And there's all kinds of subatomic particles that, you know, we relate to the proton and the neutron, but not to the electron. The electron seems to be the smallest quantum of a charge in the universe. We have never found a smaller charge carrying body than the electron. All right, now those are the units: coulombs, elementary charge, amperes. Here's a special picture of it. Now, the thing about the reason that we're talking about amperes of current is because the current or the source of the magnetic field is moving charge. But before we do that, I want to work on a charge array brain burner. You did kind of the preliminary logic and a few basic calculations over the weekend with homework. I don't know which one are we on, number 19 or something. You'll have some more homework tonight with a problem like the one we're going to do right now. And we're doing these charge array brain burners because we want to be able to do or to understand the physics of things like the water molecule. And this is a very precise picture of the water molecule. It's kind of idealized, but it's also with very specific angles and sizes and colors. All right, so go ahead and sketch this. This is a linear array. And this linear array, I want you to make a side note. Every neighbor is the same distance from every other neighbor. So they're evenly spaced. Now, I'm not specifying what the spacing is. Okay, so you could put lowercase d in there, and that would be fine. So distance d from this electron to this one, from this electron to this proton, from this proton to this electron in the middle, and then from that electron to this proton, and then from this proton over to the rightmost proton is a distance d. And I'm not specifying that. And we're not going to calculate the number of newtons using the Coulomb law, K times Q1 times Q2 over R squared. But what we are going to do is figure out the net force. So I want you to put a star next to this rightmost proton, plus 1e. This is the target particle that we want to focus on. And what we're going to do is look at each neighbor and figure out what kind of a force each neighbor produces on this target proton. So, Alexandra, this rightmost target particle here is going to get some newtons to the left and to the right. And if for every proton over here, for every electron, so all the blue ones, they're attracting this target proton. Okay, so let's jot this down. Every electron is off to the left somewhere, and it's trying to pull my target particle, this rightmost proton, over to the left. Okay, so it's going to have, when we figure out the number of newtons, it'll be a negative number. Okay, so like 75 newtons, and then we'll put negative 75 to indicate the direction. Similarly, every proton neighbor, including this one, make a note here. This one here, one proton in, that's called the nearest neighbor. Okay? This guy is out here on the edge, so he only has one nearest neighbor. If I were to focus on this proton here in the middle, he has two nearest neighbors, one to the left, one to the right. But for us, we're focusing on this baby. We want to see if it gets a net force to the right or a net force to the left. Okay? And so we have to do our accounting neighbor by neighbor and figure out, is the neighbor pushing it or pulling it? And then how big is it? All right? Now, let's say that in this one, you don't have to calculate with a distance, but let's say that the nearest neighbor interaction force here between these two babies is 98 newtons. All right, so they're pretty close. All right, and side note to yourself, it's not on the slide, but you must write this down. If you know the, lovely, thank you. Thanks. If you know the nearest neighbor force and the geometric spacing of all the other neighbors, you can figure out all the forces. It's kind of like a jigsaw puzzle. If you can get this, if you know this one, and I'm giving that to you, you can figure out all the other forces. And then you can figure out the net force. All right? So, here we go. We're going to figure out the net force neighbor by neighbor. Dude, these are the last two. Okay. Well, my TA just got me some Advil and some coffee. Hopefully this will help. Sometimes coffee helps. It's really hot. Hold on a second. Okay, that went down. Whew. All right, let's see if this goes. All right, let's continue lecture. All right, so what we're doing here is neighbor by neighbor, starting with the nearest neighbor. Okay, and here's my little tally sheet up here to the upper left. And my given information, this was authored by me, and when you're doing the homework, I'll tell you the nearest neighbor interaction force is so many newtons. Okay, and in this case, 98. All right, and so if the only other particle in the universe is this guy, this nearest neighbor, then you get 98 newtons, the nearest neighbor force, NNF, to the right. It's a push force. It's repulsive on the target proton. Right? Now, we've got a bunch of other neighbors. Here's the next one. And this one's the second neighbor. The force it produces, I denote 2NF for second neighbor force. If this were the only other particle in the universe, then it would produce a leftward pull force of attraction 1/4 as strong. And the reason for that, the distance is double. You know, whatever the nearest neighbor distance is, the second neighbor distance is twice that. Right? And that's because in this problem, not in a real molecule, but in this problem, all the charges are equally spaced. Right? So this is our simplified model of what molecules do. Okay, so if you're twice as far away, you produce 1/4 as much. Now, why is it 1/4? Because the denominator is doubled. All right, so if your denominator is 5 for nearest neighbor, okay, 5 squared is 25. But then if you double the distance, you've got a distance of 10. 10 squared is 100. Right? So your numerator is 4 times as big, and therefore the overall quotient is 1/4. All right? Now, in that case, 98 divided by 4 is 24.5. It's leftward, so we give it a negative. Right? So this is a complex series. Nothing here is very difficult. I mean, you're dividing by 4, you're dividing by 9 in the next one, 1625, and then you got pluses and minuses, and then you're adding them up. But it's easy to kind of get discombobulated. So we're just going to go nice and easy. And you're going to be doing a problem like this in just a minute on your iClicker. All right, so let's do the next neighbor out, and the next neighbor out is a proton. Third neighbor. So the 3NF, the third neighbor force. Okay, 1/3 squared is 1/9. So this one is 1/9 of 98. And that works out to 10.89. It's a push force. And here it is over here. It's kind of tiny. They get tinier and tinier, whether they're a leftward pull force or a rightward repulsion force. And this one's rightward, so positive 10.89. And that's the third force. We've got 3 of them. We got 2 more to go. Right? We got a bunch of neighbors. And as I said, we're going neighbor by neighbor, pair by pair. So one, and make a side note, pair by pair accounting. The Coulomb interaction is a pairwise interaction. Go by pairs if you have to. The target proton is a member of each pair in your accounting. You have a set of 5 different pairs. Okay? And the target proton is the rightmost member of each pair. Right? This is the third pair, and we got 2 protons. The next one, though, we have fourth neighbor pair. We got an electron out there. All right, we can handle that. Fourth neighbor force. My arrows are about the same size now. They get really small. 1/16, 1 over 4 squared. And Courtney, now I'm pulling to the left because this electron's to the left, so it's pulling my target. Okay. And it's not that big, but it's measurable. It's not quite as big as the nearest neighbor. That was 98, and it was to the right. But this one's, this one's not just chopped chicken liver. All right. So I have a leftward pull, and I've moved my accounting bucket over here to the middle now. And that's the fourth neighbor force. Now the fifth neighbor force is the 5NF, and that's the last one. And hey, you guys, you're going to have a problem just like this in about 2 minutes. So this one, the distance ratio is 5 to 1. So the force ratio is 25 to 1, or actually 1 to 25. Okay, so whatever the nearest neighbor is, divide that by 25, make it a leftward pull, therefore negative. And so in your calculator, 98 divided by 25 is 3.92, negative for leftward, and that is it. All right, now all you got to do is add them up. And when you add them up carefully to 2 decimal points, 2 decimal places, as you will do in about a minute, you get 74.34 net force on the rightmost proton. Now, if you had a different particle, like the leftmost particle, different force. If you had one in the middle, different net force. But this one, that's how you do it. If you had a particle in the middle, you'd still do 5 interactions, but some of them would be left and some of them be right now. It's even more complicated. So you can do them pairwise, interaction, accounting, not a problem if you work carefully. Now, I'm going to ask you to do one here with your eye clicker, and you're going to calculate, right? And so let me get you started here. And I'm going to turn the lights up, and Darianne and Caroline are going to circulate around and coach you up a little bit. And if you feel like you want to get coaching from Dr. B, you can slide on up here. That will work. Here we go. Calculate the net force on the leftmost electron. All right. Are we frequency BB to discuss? Okay. So now you're working on this guy over here. Okay, that's not a problem. We're still going to get some leftward push forces from all the blue electrons and some rightward pull forces from the red ones. And my nearest neighbor interaction is 1200 nanonewtons. Now this one you're going to have some whole number results for your neighbor forces. Some of them will be in fractions. Give me your answer to the nearest point something something of nanonewtons. All right? And go ahead and start. And let me turn the lights up. And definitely coordinate with your neighbor. And I'm going to drink some coffee. How about that? See if we can knock this migraine out. Karen, just talk to people. Talk to people. You've seen me do it. The nearest neighbor force is 1,200 nanonewtons. It's not 98 like the last one. Oh boy.
since it's leftward, do you go by?
You know what? I made a mistake in my I did the rightmost proton instead of the leftmost electron.
Well, that was what my question is. If I'm starting from the left, do I do it by 25 or do I do it by 4 still?
You do it. You go by the distance ratio. If the distance is twice, 1/4.
So I do start.
Yeah. So no.
So
I mean,
it doesn't matter which way you're going.
doesn't matter which
Okay.
way you start.
All right, thank you.
The answer, is it okay if we have it in nanometers, or did you want it in
Just
meters?
a whole number.
Just a whole
And can you bring your calculation up here so I can check? Could you write it down?
Yeah, we wrote it down.
Who's got it written down? Yeah, let me see your calculation.
This is what we got down at the bottom.
All right, let me see what you got here. Come on around here. Let's take a look. Oh, do you have a question?
Yeah.
Come on around here.
I forgot my clicker. Am I just pretty much screwed?
Yeah, it's just one question today, so you'll be all right. Don't worry about it. All right. Are you coming up here or what? You slacking on me? This the whole semester. You want to make it an entire semester of slacking?
All right.
Question.
Okay. So you started. This one was 1200, and would this be
No,
1/2?
no. Just the first interaction is 1200.
So this would be the 1200.
No, no. The force from this one, this pair produces 1200 newtons this
In
way.
front of the class.
Okay.
See, a second
On
ago, we
this
didn't
one.
even understand
Okay.
this.
And
It
then
makes
this
so much
pair
more sense.
I think that
is
it just
300
helped me, like,
newtons.
I don't know. Sometimes we just talk
1200
about when I'm
divided by
writing it,
4.
and then when we
Right.
do an
That
example
way.
problem, I'm like, okay, what happened?
Okay, but you don't really
But you're
say
writing it
that
down,
the
but it doesn't
charge
process it.
is
Yes.
1200 or 600
It
or
helped me
anything.
to, like,
What you say is that's not right. It's got to be, remember, it's 1 over n squared.
That definitely
Okay,
helped
it's
me,
1
'cause
over
I was
2 squared, 1
confused
over
about
3 squared, 1 over 5,
So
4
this
squared.
is the 1 over 2 squared. This is 1 over 3.
No, this is 1 over 1.
Yeah, it's all
This-
about those
Okay.
numbers.
That's
and little
the one
vowels.
that's just, and this one's 1 over 4, 1 over 9, 1 over 16.
Okay,
So,
this
yeah,
process
and then you got to decide the directions and stuff. All right, I'm working with these guys
All
here
right,
now.
cool.
All right, so let's check this out now. Okay, this one is 300 leftward, so it's minus 300, total of 900.
Right.
Positive. Okay, now this one is 9s, so 1200 divided by 900. Okay. 1200 divided by 9. It's negatory. Okay. Right?
Yeah,
Yep,
yeah, we're
that's
right.
right so
We're
far.
right so far.
And then, let me get
Hope it
this other one
stays
here.
that way.
No, it's, I have the answer here ready, but it's for this target instead of this target. So I have to redo it. Okay, so now this one is gonna be a pull force to the right, 1, 2, 3, 4. So 1200 divided by 16, 75. Okay, do you have that?
Yeah.
Very good. All right, now the last one is 1200 divided by 25. It's 48.
Come on.
So that's 3, 8, 12. Okay. So plus 75. Oops. Let me do this again. 48 plus 75 plus 900 minus 1.
Oh, so it
There we
is
go.
the same answer.
Oh, so my answer, what?
Your answer is la correct.
I must have done it correct. Okay.
Yay!
I did it correctly. Okay, we check. Good.
Yeah, it was good.
Yeah.
That's the scientific.
Good. Nice.
I'm trying to figure out how to set it up so that I can basically do it myself. But what me and my partner are confused on is we know that it's gonna be 1/4, then 1/9.
No, the first one, nearest neighbor is 1 over 1.
Oh.
So that one you just,
Okay,
yep,
then
then
1-4,
1-4, then 1-9,
1-9,
right.
1-16, 1-25. That's all I need to know. I can figure it out now. Thank you.
Plus, don't forget your minuses and pluses. Your lefts and your rights.
Okay.
Lefts are positive.
So since this is an electron, then we're going from left to right, right?
Yeah, so this is
So
my
this is
target. This is a proton, so it pulls to the right.
this will be positive.
So positive 1200
Then
newtons.
negative.
And this one will be negative 300 newtons. Blah,
Negative,
blah, blah, blah.
negative.
Yeah.
Positive, positive. Okay.
Right.
All right, I'll be back.
Okay. Question. What is your name again?
Gabriella.
Gabriella what?
Hold
Okay, good.
on. For the
You
first,
sit up here every day.
going from negative to positive, would it be negative 1200, or do we
No.
keep it the same?
No, this is what makes it tough. This is your target, right? Okay, so you're asking, what is the effect of this particle on this target point? It's positive. It's going to attract it to the right. So this should be a positive here.
Did I do all the signs wrong?
It looks like it, because this is negative, right? And so it's going to repel this one. It's over here. It's pushing this one away. Okay,
So that one
so
is
that's
going
like pushing
leftward?
you, yeah,
Yeah,
that way.
so this one would be leftward. So it would be negative.
Negative, right? So this one is like,
Oh.
okay, so this one is like,
Yeah.
okay,
totally.
only that one,
Yeah.
positive.
Okay, so when they're the same sign, they repel, so it's gonna go
That's right. When they're the same sign, they
to the
repel.
left.
That's right.
And then when they're
Yeah, but you
opposite,
can't
to the
say
right.
it's. What you have to decide, it's independent. Whether they repel or retract is independent of what direction they are. In other words, you may have a repulsive interaction, but the repulsive force might be a push to the right, or it might be a push to the left. Remember this, when we did this one, the repulsive force was to the right. But for this one, the repulsive forces are to the left. So you can't just say all repulsions are left. You got it? And that's why it's tricky.
Okay, so it all depends on the target.
It does depend on the target and where your other particles are. If they're all to the right, attractions are going to go right, repulsions are going to go left. This one, when we first did this one, when this was our target, all the particles were off to the left.
It was opposite.
So, right, so attractions were to the left, but repulsions were to the right. So it depends on, you just have to study it very carefully.
Okay, that's what confused
There's a
me.
lot of, it's a lot of decisions to kind
Yeah,
of
'cause I was
sort
doing
through.
it the same way as the other one, but I forgot. Okay. All right,
Right?
thank you.
Right. Whoa, you guys are crushing it. Woo! This is one of the harder ones too. Very nice. Oh, wait a minute. I blurted out the answer over the. You didn't hear? I blabbed out the answer. Okay, 1 minute. You've had 15 minutes already for this one problem. And Caroline, where did Caroline go? Thank you. That Advil did help, really, in this coffee. My head only feels like it's semi-exploding. It's an improvement. Amber, 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 amber. Feeling better. I'm feeling human again. Yeah, the Advil's helping. No, I don't see stars. I just feel pain from light. 30 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, we got this. Okay, let's take a look at what we got. We have some answers here. We got a whole bunch of answers, but let me zip down to the. Here's some people. This is where the right answer is. 889.67. Let me move this a little bit. Oops. Let me go back. Okay, there's your answer, and a bunch of you got it. Now, you guys up here, you rounded off incorrectly. And you guys down here, you rounded off incorrectly. So you might get partial credit on that. But you guys, what's the percentage on that? Does it say? 61%? No. 65%. Very nice. You guys, uh, you just made the record for excellence. I've never had a class, not even when Darian was in it or Caroline, that crushed this big of a problem basically on the first day I gave it to you. So that's pretty good. But can you do it for homework? All right. Time will tell. All right, now, why are we doing this? Because it's going to help us, as I said, understand what atoms, especially atoms in molecules, do. Now, we still need some insight on magnetism and electromagnetic waves. And so let's turn to that topic. We'll just do a real, very, very basic introduction to the magnetic field and the source of the magnetic field. And then we'll do some sketching on the document camera, and I'm all set up for that. So the basic idea is if there's a current, there's a magnetic field. And the magnetic field is set up around the current itself. So we say that a moving electric charge is the source of a magnetic field. The simplest case is a straight line current. If you're going from A to B, then you set up a magnetic field. The next simplest case, and we'll graph up or sketch out both of these two cases, a circular current, or what we call a current loop. And this one's important because all electronics have to have current going in some kind of a closed circuit, a loop. They go from point A to point B and then back around to point A. Otherwise, current will not flow. And so every electronic circuit is going to generate a magnetic field. If the current is oscillating, the magnetic field will be oscillating. It gets rapidly difficult. Here's another cool factor. A spinning charge can also generate a magnetic field. All right? So an electron that spins, we can say that it has a magnetic field as well. Let me just check something out here. We're going go ahead and jot those down. We're going to do some sketch work now on the document camera. I'm just going to bring my computer over to the side here. I'm going to keep recording, but I'm going to, at this point, go to the document camera, and in the podcast, I'll insert a PDF scan of the sketching that I'm about to do with you. So let's go ahead and do that. And before we do anything else, let's do the electric field of a stationary proton and a stationary electron. Let me swap over to the document cam. Okay, so here in the lecture hall, we're on the document cam, and it's been one of those days, I guess. But this stuff is going to be recorded in and jotted down. Okay, so here's our sketching task. Let me bring this over a little bit closer. Okay, here we go. Now go ahead and draw a circle to represent a proton. All right. Now a proton is not a billiard ball, but a lot of times you represent it that way. The electric field of a proton is directed outward symmetrically like spokes of a wheel. And I'm putting 6 spokes in this electric field. Okay? And these are what we call the electric field lines, E. And it indicates the direction that a small positive test charge would accelerate. Okay, in other words, the net force. So if you were to put a little teeny positive test charge out here, like this little guy here, okay, that little positive test charge, it would be repelled, and it would be repelled straight away from the proton. So this little teeny positive test charge right here that I penciled in, that would be repelled away. Now if you put one over here, a little teeny positive test charge so small, it's barely there, but it's positive, it would get repelled off, it would get accelerated off in that direction. Okay. If it's in motion, its velocity will change in that direction. Okay, it'll start slowing down or speeding up depending on what its initial velocity is. But anyways, that's the electric field. And this is what we call a monopole. One pole of the electric field. Now, go ahead and draw a circle to represent an electron. The electron is different. If you put a little teeny positive test charge over here, right up here to the northeast, it would get pulled back down to the electron because they attract. So the field lines are directed inward, and they're symmetric. And because we have the same amount of charge, we should draw it with the same amount of field lines. So I'm drawing 6 inward field lines. Okay? So every time you have a positive, the field lines go outward. And if you have a negative, the field lines go inward. Now here's a bonus sketch. These are monopole fields. Let me give you a bonus sketch. A dipole. Okay, the dipole field, put a plus and a minus next to each other, left and right. Now, draw in 6 inward, field lines for the negative charge, all right, and 6 outward field lines, but just a little bit of the field line. All right, now if you have 2 charges like this really close to each other, the field lines blend together. All right, now look at this central one. Between the 2 charges directly on the line between them, that's a field line, a single field line. It starts going outward from the proton and it lands going into the electron. Nice. This one, take a look at this one. The northeast field line for the proton. And here's the northwest field line for the electron. And guess what happens to those two? Ching! They kind of gracefully go in like that. And the same thing down here. And I'll put my direction down here. I'll put a direction here. Now, go to the northwest field line. Here. The northwest field line of the proton, it's going out to the northwest. The northeast field line is coming in from the northeast, and guess which one it hooks up to? This one over here. And there's a huge amount of calculus in all this. But yeah, these field lines. And then these ones down here, southwest from the proton connects around to southeast from the electron. But right here, along this, see where my pencil is? Along the symmetry line. There's 2 symmetry lines. There's a horizontal one and a vertical one. Along the vertical symmetry line, the electric field is always to the right. Okay, now this one goes out to infinity. So you can put the, and this one comes in from infinity. Right? And that's what a dipole field looks like. My wonderful students, a bar magnet has a magnetic field that looks exactly like that, a dipole magnetic field. Let's start talking about magnetic fields. Okay, here's the first one, straight line current. So here's your, let's just say that your current, capital I, is flowing in that direction. Okay? And let's do a view directly down. This is a second view. And we'll say that this X indicates that the current is into the paper. Okay, so this is a perspective view. Okay, and this down here is an end view. We're looking right down the pipe on this one down here. And this one down here is the easy one, but I'm going to sketch up here first with a perspective view. The magnetic field lines for a straight line current form circles. Okay, and at every point along the line, there are magnetic field lines. Okay, and there's 2 sets of electric field lines. And in this case, the field lines would be directed like this. Okay? And right here, where there's a gap in my drawing, okay, right here where there's a gap in the drawing, that means the field line is behind the wire. Okay? Over here where there's no gap, it just goes across the wire, that means the field line is in front of the wire. You see the field line and then the wire itself. Same thing over here. The magnetic field lines are always loops of some kind or another. Here's what it looks like if you look at it. Okay. Draw concentric circles. And one arrow. Now you may be saying to yourself, hey, Dr. B, how do you know it's going clockwise like that? To know the direction of the magnetic field lines, you have to use the right-hand rule. Okay, now I'm not going to try to draw it on the sketch here, but I am going to try to show it to you using my right hand. Okay? You put your thumb in the direction of the current, and then the field lines curl. You put the arrows in on your field lines in the direction that your fingers of your right hand curl. Okay, so now in this case, Logan, my thumb goes right into the paper, because that's what this means, eye into the paper. So my current eye is into the paper, and my fingers go around clockwise. Now, if I had current coming up from the paper, is it time to leave? All right, hold on. What? Okay, hold on. This will be our last sketch. If I had current coming up from the page, then I'd still use my right hand, and the lines would go counterclockwise. Homework tonight. You're dismissed. See you Thursday. Be ready to have your brain burned to a crisp. All right, so we got to this straight line. I should have asked you guys to help me with this podcast here. Okay.
Having your office hours tomorrow?
Yeah, that's correct. I'm not.
Gonna be on campus at all tomorrow?
No.
No. Probably
Timesheets.
day, yeah, because I don't have mine right now.
I'm going to leave as soon as I can. In fact, I might leave right now.
Yeah.
Yeah, to make sure I don't have a relapse. You saved the day. I'm not kidding. You did a nice favor for me. You went way beyond the Call of Duty.
For the SSG, do we need to print out the paper again saying where we're going to be? Or can
No,
we
just
send
text me, and it would just send me a message.
Is the final review cumulative or just?
Final exam is cumulative, yes.
Okay, well, thank you.
Yep, you're welcome.